All right, so as promised, I would like to share with you a little bit easier method to do a transient analysis. And not only is it a little bit easier in my estimation, I also can tell just by looking at it that it's a little bit more powerful. And I'll kind of mention what those ways are that makes it a little bit more powerful as we go through some of these steps here. I know it's a lot of text, but kind of bear with me. I'm going to step through what we're doing in each one of these steps before we get started with our actual problem. So first of all, you'll notice I've got it split into two columns. One is for RL circuits and one is for RC circuits. The reason I have it split into two columns is that the two columns are almost identical to each other, but they have subtle differences. And so I wanted you to have a version where you're doing an inductive circuit, and I wanted you to have a version where you're doing a capacitive circuit, right? But the steps are almost the same as each other, so I just set them side by side with one another so you could see how they work. So step one is you have to take your circuit, turn off all of the independent sources, and then evaluate what the equivalent resistance is seen from the terminals of the inductor or the capacitor, whichever one you're dealing with, right? So you look across the terminals of the inductor or the capacitor, kind of think about removing the inductor or capacitor from the circuit and evaluate what the equivalent resistance would be across those terminals, right, with the independent sources off, okay? So that is step one, is to find that equivalent resistance. And then occasionally you'll be dealing with a circuit where you only have like one inductor or only one capacitor. And in those cases, you would want to just take that value and use it as LEQ or CEQ, whichever one it's appropriate. But in other cases, you might have some network of inductors or some network of capacitors, in which case you would have to use our combination techniques that we have been talking about in here already to come up with what an equivalent inductance or an equivalent capacitance would be for those little networks. So that's step one, is find those two values. Next, you want to, in the case of an inductor, you want to view that inductor as a short circuit and then do a steady state analysis to come up with what the current through that inductor is right before the state changes, right? I sub L at time 0 minus basically says what was that current through that inductor right before the interesting change in state happened that we're constantly talking about with these transient analyses, okay? In the case of capacitors, you say what was the voltage in the capacitor right before we did something that changed the state of the circuit, okay? So that's kind of the same in both cases. It's just that you're finding it a current in the case of an inductor, and you're finding a voltage in the case of a capacitor for step two there. Okay, step three, you still leave an inductor as a short circuit if you're doing an inductor, or you leave the capacitor as an open circuit if you're doing the capacitor. But now what you do is you find what value interests you as time goes to infinity. This is where this technique gets more powerful than the one that I just showed you, okay? Because we don't care what effect we are analyzing. We can look anywhere in a circuit. In other words, a circuit, one of the things you can look at is current through an inductor or voltage across a capacitor, and those are interesting, but a lot of times that's not what you care about. You might care about the voltage or current somewhere else in the voltage or in the circuit network, and if that's what you care about, this technique allows you to directly find what that effect is, and it doesn't have to be voltage across a capacitor or current through an inductor. Does that make sense? But what you're doing in this case is you're saying, if we allow time to go on to infinity, what are the values going to be for this location of interest? It's typically a voltage or a current somewhere in the circuit that you are tasked with finding, right? And you say, what is that going to be as time goes to infinity? Okay, you with me so far? Once we find that in the context of setting up this list right here, I'm going to generally call that thing that you're finding F at infinity. I'm using F there because it could be voltage, it could be current. It's some function of time. That makes sense? All right, step 4, we have to kind of bring in one of our little thought processes here, and that is we know that current can't change instantaneously in an inductor. Also, we know that voltage can't change instantaneously in a capacitor. So that means that for an inductor, whatever current we had flowing at time 0 minus, that had better be the same current that flows at time 0 plus. Okay? So what you can do is, since you found what this current was at time 0 minus up here in step 2, you can bring that up to step 4 and say, not only do I know that current at time 0 minus, that carries forward into time 0 plus. Right after the change occurs, that is still going to be the current flowing through that inductor. Okay? The equivalent of that for capacitors is that whatever voltage you had right before the change is going to carry over to being the voltage that you have across the capacitor right after the change. Now here's my big point that I need to tell you to be careful about right here. You are not doing this step number 4 at your location of interest, right? What you are doing is you are applying that effect at the inductor or at the capacitor, and then you are doing an analysis using that to figure out what your effect is that you are actually interested in. So there's a little bit of a circuit analysis you got to do here on step 4, and what it actually comes down to is that if you have an inductor, you figure out what that inductance or what that current value is going to be right after the change. You can treat that like it's a current source and then work that circuit's problem. You would basically replace the inductor with a current source and then work that circuit's problem, where that current source has a value that you found in step 2. Okay, we'll do an example here in a few minutes, and that'll hopefully make perfect sense to you. But I did want to say you have to be careful here, because what you're doing is you're using this effect at the inductor so that you can find some other value somewhere else in the circuit. Okay, the step 4 for capacitors is actually very similar. It's just that your voltage in your capacitor carries over, and you can use that. You can treat it like it's a little voltage source at the location where the capacitor was to figure out the effect that you're interested in at time 0 plus. With me so far? Okay. In either of those cases, we are going to have, we're going to use this term right here, F at 0 plus, to denote that value that you are finding. Okay. Now, step 5, I kind of mentioned this a second ago, but we also need to know what the time constant is for the circuit that you are dealing with. The time constant for an inductive circuit is just the inductance, the equivalent inductance value divided by the equivalent resistance value seen from the terminals that the inductor is hooked up to. With, I should say this too, with the independent sources turned off. That was all the way up at step 1. Okay. Finding the time constant for a capacitor is very similar. It's just that you take the product of the equivalent resistance and the equivalent capacitance, and that gives you that time constant. And in either case, we'll just call it tau. Okay? Once you get done with step 5, you have now essentially collected all the values that you need to plug into this equation. Whatever circuit parameter that you're interested, typically it's a voltage or a current, whatever parameter that you are interested in is going to be equal to that same parameter, whatever that parameter approaches as time goes to infinity, right? I had that highlighted in yellow up here. So whatever that value is at time, as time goes to infinity, plus the difference between whatever that value started out as soon as the switch is flipped, right after the switch is flipped, whatever the state was that changed, right after that state changed, minus whatever the value is that you have going to infinity, all of this multiplied by e to the minus t over tau. And this equation works for both columns. Once you've figured out each of those little things to plug into that equation, you know, writing the equation is actually relatively simple. Okay? So I know some of this might be hard for you to picture until we do an example. So that's what I'm planning on doing next, is an example to kind of demonstrate how to use this process. Okay, we good with that? All right, here's the example. The switch shown was closed for a long time before opening at t equals 0. Okay, what is that? Why is that statement in the problem? That's to give you confidence that, okay, that's to give you confidence that the inductor was in some kind of a state where it was at its steady state before the switch opens, right? So there was nothing else sort of changing or transients happening because it had been in that state for a long time. Meaning that inductor over there is going to behave like what in that, like right before the switch flips? It's going to behave like a short circuit, right? That's what an inductor behaves like in a steady state condition. Okay? It says find the voltage across the 20 ohm resistor as a function of time for t equals 0 minus, and then also for t greater than 0. Okay? Now, here's where this is interesting, and you know, some of what may have confused you when we were going through our steps just a second ago is you're like, I'm not sure what F is. Okay? And that's because I needed a general way to write it. In this problem, the F that we are trying to find up here is what? The voltage across the 20 ohm resistor as a function of time. That is the F. That's the value of interest that we are trying to figure out. And it's typically, at least in the context of engineering problems like this, it's typically the thing that the problem asked you for, right? So that's what I mean by F in that you know, set of steps that I gave you up there a second ago. Okay, so let's start with our steps, right? I gave you a set of steps. Let's start with doing those. What was step 1? So turn off all the independent sources, right? And we want to do this also where it is in the state after the change happened. Okay, so we're doing this sort of not before the switch flipped, but after. Okay, so how do I draw this if I'm going to, let's say, try to figure out the equivalent resistance? What state is the switch in after it changes? It's open, meaning what about this little leg up here up top? It's like it goes away, right? There's no path for current to flow up there. And so what we end up with is a circuit where, actually, let me say this too. We're supposed to turn off the independent sources. What does that mean for the 10-volt source? It becomes a short circuit. So where I had that 10-volt source, it becomes like it's just a wire. I have my 20 ohm resistor here. I have my 80 ohm resistor right here. I don't have a path going up over the top through that 100 ohm resistor anymore because the switch is now open. I have a resistor over here that's a 60 ohm. This comes down to where it would have connected to my inductor. What I need is what is my equivalent resistance across these terminals. Okay? Is that hard? No, that's pretty easy, right? How do you do that? Well, there is a series connection through this 60 ohm resistor that connects up with a parallel connection between my 80 ohm resistor and my 20 ohm resistor, right? So that means if I want to do it all in one step, I can just say 60 ohms plus 80 and 20 in parallel. That would be that expression right there. And if you work that out, which some of you I believe might be doing right now, I think what you will end up with that is 76 ohms. Okay, so that is the equivalent resistance that I need in this problem to do things like find my time constant, for instance. Okay, what about my equivalent inductance? Easy, right? Why? There's only one inductor. So whatever that inductor value is my equivalent inductance. 500 millihenries. Half a Henry. Okay? Now, we're done with step one. Okay? But we're not going to take a break. We're going to press on. What do you want to do next? Step two. Okay? Step two says, viewing LEQ as a short circuit, do a steady state analysis to find the current through that LEQ at time 0 minus. Okay? So what does this circuit look like at time 0 minus? I have 10 volts here. It goes through my 80 ohm resistor, goes down through a 20 ohm resistor. At time 0 minus, what state is the switch in? It's closed, right? So meaning I cannot ignore this extra leg that I have up here. Okay? But because this thing has been in its steady state condition, it's been in this condition for a long time, right? What do I do about this inductor over here? Okay? It's just a short circuit, because after a long time, inductors behave like short circuits. Now, what I'm supposed to find is what kind of current is flowing through that inductor that is in its steady state at time 0 minus. Where should I draw that on this picture? That goes right here, correct? Okay. And so I'll go ahead and label this as I sub L 0 minus, right? Because that's what we're coming up with there. How do I find that? Well, there's not probably just one answer to that question. There's probably multiple answers to that question. But what's your preference? I'll give you, if you're not going to have a preference, I'm going to have a preference. Okay? I like mesh for this. Okay? So if I'm going to do a mesh analysis, how do I start? Okay? I first identify my meshes by showing my mesh currents. So this one is I1. Let's call this one up here I2. And this one over here is I3. One of the advantages of doing mesh here is what is IL at 0 minus relative to my mesh currents I just defined? It is I3. So once I find I3, it will be this value that I'm trying to find over here. Okay? So those are my mesh currents. Now what do I do? Okay? What I probably want to do is write my loop equations. I'll start with this loop down here in the lower left-hand corner. There I've got minus 10 volts plus I1. Well, I'll do 80 ohms first. 80 ohms times I1 minus I2. Then what? Plus 20 ohms. Okay, times I1 minus I3. Then what? That's it for that one. Okay, now I'll do my second loop. For the second loop, I'm just going to have 100 ohms times I2 plus 60 ohms times I2 minus I3 plus what? 80 ohms times I2 minus I1. And that should all sum to 0. Then what? For I3, I'm going to start with a 20 ohm. Okay, that multiplies by what? I3 minus I1. Okay, to this I'm going to add 60 ohms times I3 minus I2. This gives you a 3x3 system of equations, and you're hopefully getting good at doing that kind of work. What you should get out of this system of equations once you solve it is that I1 is going to be equal to 0.2053 amps. I2 is going to be equal to 0.1 amps. And I3, which is the one that we really cared about, right? That one is going to be equal to 0.1263 amps. All right. So what is IL at 0 minus? 0.1263 amps. Now, you might think that we're done with step 2, and I guess technically we are done with step 2. But I do want to touch on something else here before I leave this point. One of the things that the problem asked us to find up here was the voltage across the 20 ohm resistor as a function of time for t equal 0 minus and for t greater than 0. One of the things that we will not get out of our function that we write, because that's what we're shooting. This whole technique is shooting at trying to find this function up here. One of the things this function won't tell us is what the value is at 0 minus. What do we have to use if we need that number? We really have to use this same diagram that we have in step 2 if that's something that we want. And good news is it's easy. We just have to do it if we want it. So how do we do that using this diagram? Okay, let me first of all define what direction I'm going to kind of assume this voltage is going to go. Let's say that I'm assuming the voltage is going to go here, and I'll call it V20, right? So V20 at time 0 minus will be what? 20 ohms times I1 minus I2, right? So this is just going to be equal to 20 ohms times I1 is 0.2053 amps minus 0.1263 amps. And I should have written that here as well. Okay, so what does that give me? 20 times 0.2053 minus 0.1263. 1.58. Okay, how you feeling? Okay, shall we truck along and get to step 3? Okay, step 3 says, still viewing LEQ as a short circuit, do another steady state analysis to find the value that interests you as t goes to infinity. Okay, so what should my circuit look like in this case? Okay, we're doing now time going to infinity, meaning The switch is now open, which means all we have is an 80 ohm resistor here, a 20 ohm resistor here. Okay, this was 10 volts here. And then over here, we're going through a 60 ohm resistor. And then going through a short circuit is how we're going to model the inductor. Right? It says still treating it like a short circuit, do another steady state analysis to find the value that interests you as t goes to infinity. And then I put down on the notes, it can be something other than the current through your inductor. What is it in this case that's our value of interest we're trying to find? Okay, what we're trying to find is this value right here. I'll call it, again, V20. We're trying to figure out what is that value going to be as time goes to infinity. Okay? What technique do you like for this? I'll tell you what I like for this. I like the idea of going a little bit old school. Okay? Here's what I mean. We can define a source current. Let me just call it just plain old I. What is that source current going to be? Should be 10 volts divided by whatever our equivalent resistance is. What is the equivalent resistance as seen by this 10 volt source? Well, that current all of it has to go through the 80 ohms, but then it splits and some goes through the 20 and some goes through the 60. So how do I figure out what the equivalent resistance is in that scenario? Should be 80 ohms plus what? 20 and 60 in parallel, right? So that would be like 20 ohms times 60 ohms over 20 ohms plus 60 ohms. I punched that in earlier. Hopefully I did it correctly when I got 0.10526 amps. Now that is not really ultimately what we want. What is it we really want? We want V20. How about this? What if I come up with I20, meaning the current that flows through the 20 ohm resistor? Okay, is there a way I can get that easily? Current division. I20 is going to be equal to that current we just found, 0.10526 amps, multiplied by 60 ohms over 20 ohms plus 60 ohms. And that result comes out to be 0.078947 amps. Now, is that what I wanted? Still not quite there. What else do I need to do? Okay. If I want V20, and this is really what I'm trying to get at, right, is V20 at time equal infinity. What do? I take I20 at time equal infinity and multiply it by 20 ohms. Okay. That looks to me like it turns out to be 1.5789 volts. Okay? All right. Any questions? Did that one make sense? Are we ready for step 4? Ready or not? Let's do it. Step 4 says, since current cannot change instantaneously in an inductor, use IL at time 0 minus equals IL at time 0 plus to find the value that interests you at t equals 0 plus. Okay? So what we have to do is take our circuit after the switches close. Okay? This is at t equal 0 plus. Right? So we still have our 10 volt source over here, still going through an 80 ohm resistor. This comes down through a 20 ohm resistor. Goes over here through the 60 ohm resistor. But now, right at time equals 0 plus, at that instant in time, it is like we have a current source over here that has the value that we came up with in step 2. What was that value? 0.1263 amps. What direction? Down. So that means I go down here and I say it's like we have this 0.12, what was it, 63 amps current source right there at this instant in time. Now I'm trying to be careful about how I say that, because if you go any time after 0 plus, it won't behave like that anymore. But right now at this time, it's behaving like that. Okay? All right, so what are we supposed to find? We are supposed to find the value that interests us at t equals 0 plus. What is the value that interests us? V20. So what technique do you like for this task? Or do you want me to pick? Okay, I'll pick. I like nodal for this task. Okay? Now there's an argument could be made that some other ways might be easy too. So I'm not discounting other ways of thinking about it. But let me go ahead and identify some nodes, the bottom one here being my ground node. Let me identify a node up here and another node here. And then I'll do a third node over here in case we're interested in that. All right. Would I have any supernodes? Where do you have supernodes? Like how do you know when you should come up with a supernode? Okay. Supernodes happen across voltage sources, right? So what I would say is that we actually have a voltage source connected to the ground node here. So that means we're going to kind of treat all of that as one big super ground node, right? So the next node that I would want to write some equations for might be the one up there that I colored blue. Let me write some variables as well, because I didn't do that part yet. Let me call this V1, V2, V3. Let me do my node equation, my Kcl equation for node 2. Sound good? So what I have there is V2 minus V1, because we're talking about currents that are exiting the node typically when we do this, right? So we're going to take exiting as being positive. So the current that exits to the left across the 80 ohm resistor is going to be equal to V2 minus V1 over what? 80 ohms plus V2 over 20 ohms plus what? You could say V2 minus V3 over 60 ohms, but is there something easier than that? How much current has to flow through the 60 ohm resistor? 0.1263 amps. That looks like it's easier to just plug that in directly and say that's 0.1263 amps. Furthermore, what is V1? V1 is set at 10 volts by this 10 volt source. So if I want, I can just go in here and say that's 10 volts. Okay, how many unknowns am I left with in that equation? Just one, right? That is good news, right? Because that tells me I should be able to solve for V2. Okay, which, I think the easy way to do that is just to pop it in here where we do x being our variable. So x minus 10 over 80 plus x over 20 plus 0.1263 is equal to 0. Shift solve. That ends up giving us negative 0.0208. Before I move too much further, what we just found is what? Okay, that is V20. And it's V20 at what point in time? At 0 plus. And it's equal to negative 0.0208 volts. And I want us to, not miss something as we're moving along through here. What was V20 at 0 minus? Okay, that was we have 1.58 volts. So what just happened going from time 0 minus to time 0 plus? We just had an instantaneous change in voltage across that resistor. Does that cause us worry? Does it need to? Okay. Let me explain why it might need to in some cases. We don't know for sure if it needs to in this case. If that voltage is also directly applied across a capacitor, does that cause us concern? Okay, it should, because that can't happen across a capacitor, right? You cannot have an instantaneous change in voltage across a capacitor. Can you across a resistor? Yeah, there's no rule about that. So you can have instantaneous changes that happen in your circuits. You just have to be wary of the two that can't happen. What are the two that can't happen? Instantaneous current change in an inductor and an instantaneous voltage change in a capacitor. We don't have either of those happening in this case, and so we're not concerned. Okay, so but I figured I'd point that out so that we can at least see it, and if you end up seeing an instantaneous change somewhere in your circuit, if that causes you some worry, you can process it. All right, what do we have next? This is an easy step. Step 5, time constant. What's our time constant? It is going to be LEQ over REQ. So for that, we want to do 500 millihenries, which is the same thing as half a henry. And a henry is what? Okay, it's an ohm second. Divided by my REQ, which is 76 ohms. So the units of this do come out in seconds. That makes us feel good, because it should, or some unit of time at least. What does it give us? Okay, 0.0065789 seconds. Or if you want to convert this into milliseconds, how would you do it? Okay, milliseconds, you move that decimal 3 places. This is just going to end up being 6.5789 milliseconds. And we're almost done. What's our last step? We write this equation, right? What is our value of interest at time infinity? It was up here, 1.5789 volts. And we're talking about V20 as a function of time, 1.5789 volts, plus, what do I put in the parentheses here? We're building this off of this function way up here. F at time 0 plus. What was that? What's next? Minus f at infinity. And f at infinity was 1.5789 volts. Then what? E to the minus t over 6.5789 milliseconds. What do you think about that? Could you plot that if you needed to? Yeah, everything you need is right there. You could plot and see what this voltage did as a function of time for time greater than 0. All right. Any questions? All right. Well, thank you for your attention.